here's what I want to talk about today. Boiled down to one sentence. This is the goal of the research. By the way, spoiler alert, we have not accomplished this goal yet, but here's the goal that drives the research. Today, if you ask how many people can control what their computers really do, that is, program their computers, the answer is about, I estimate, 1% of humanity. That's the bunch of us, including most of you and me, who have taken the time to learn the language of computers, you know, like PL1 or Java or something, whatever. The goal of this research is, why don't we instead have computers learn the language of people so that we can just program them or teach them in the way that we teach each other? So it's a simple goal. You can see that if the field could achieve that goal, it would fundamentally change the way that humanity interacts with computers. Because right now, most people, for example, most people have one of these, and we wait for engineers at Apple or Google or somewhere to add the functionality that we want. But if you think about the functionality you individually could have if you could easily teach or program this, you could make it way more useful than it is. So that's the goal of the research. It's a very simple goal to state. And I should point out, the reason there are so many names on this slide is that what I'm going to talk about is actually joint work with all of these people and more. It comes, I guess, as preface. I also want to say, sometimes people say, well, gee, machine learning is moving fast. Where is it headed? My personal impression is that it's easy to predict the future of machine learning. All you really have to do is look at how people learn, and computers don't yet. And so, for example, most of the work in machine learning today is about function approximation. With some function we want to learn, like maybe classify emails yes or no as spam, or classify a patient yes or no as having pneumonia. But people learn in way more ways than statistical function approximation from passively acquired data. People learn from instruction, from demonstration, from experimentation, also from passive observation. But they learn in so many different ways compared to machines today. So if you want to think about the future of machine learning, how might it be different in 2028 from 2018? Seems to me, here's a menu of kinds of learning that humans have already proven is possible, but we haven't gotten around to figure out how to put into machines. And so one aspect of that, of course, is that we learn from instruction and from conversational instruction, which is the focus of what I want to talk about. Okay, so to frame this, I'm going to talk about the problem in the context of sensor effector agents. That's a pretty broad context. So again, if I had a cell phone, I might characterize it as a sensor effector agent with both some physical sensors, like microphones and cameras that sense the physical world, and effectors, like it can vibrate in the physical world, but also cyber sensors and cyber effectors. For example, it can read the web, it can send messages, and so forth. So I could think of a mobile phone or a robot as some kind of sensor effector agent. And what I'm interested in is, to what degree can we use conversation and other methods to teach these sensor effector agents procedures that we want them to follow. So to think about that a little more precisely, I want to start by defining what I'll call the sensor effector closure of such an agent. Let's just say that's the set of all operations the agent can perform in its environment, given that it only has those sensors and effectors. So it obviously can't change the world in ways that it doesn't have effectors to do. But But if you imagine a sensor effector box, and you could put any computer program inside there, any computable program inside there, then together with its sensor and effectors in the environment, that defines a space, Venn diagram of all possible sensor effector agents that could come out of that. And like our cell phone will never be able to ride a bike. It just doesn't have the effectors for that. But there are a lot of other amazing things it could do because it can read our email and write emails on our behalf and so forth. Okay, so I think it's just useful to think about the notion of a sensor effector closure of a system, and both in terms of machine learning in general, but also in terms of conversational agents, thinking about, well, what would it take? What would be a sufficient initial structure to put inside this sensor effector agent that would then make it possible, at least, that we could teach it arbitrary other things to do. So it's kind of a framing of the question. All right, so our research goal, of course, is to be able to teach the agent anything that is in its sensor effector closure. And part of the research question is, what's the initial structure we've got to put inside this agent in order for that to be the case? Or are there, well, let's just leave it at that. So now, just to get your creative juices going, think about what are the kinds of things that are in the sensor effector closure of your phone. Well, here's one. Whenever I have to catch a flight, alert me to head to the airport so that I'll be there an hour before flight time. And it turns out Google engineers actually thought of this one. Thank you, Google. And for a couple of years, I've had this on my phone now. I'm very happy. It's something the phone could do, and in fact, the programmers out there thought of it and gave me that capability. But there are lots of other capabilities like that that I'm still waiting, and some of that I'm going to wait forever because they don't know me, they don't know what I really want, and besides, I'm a small market, so they're not going to do it for me. This is partly to argue that we want users to be able to add their own capabilities. What else? If you live in Pittsburgh, then a useful thing is whenever it snows at night, set my alarm 30 minutes early. Not because I love getting up to see the snow, but so I won't be late for work. Okay? And again, well, the Google engineers and the Apple engineers haven't gotten around to give me this one. Here's another. If somebody sends me a picture containing my mom, forward it to her. She loves that stuff. And well, nobody's given me that one either yet. Whenever a student sends email about a homework question, forward it to the teaching assistant who wrote that question. You laugh, but that is in the sensor effector closure of my phone. There's no reason I couldn't have that functionality. If Google engineers and Apple engineers and so forth got around to it, they could write a program to do that. But they're not. They haven't. And they're not going to this year either. So some of these examples kind of suggest, I think, why it would be very, very useful if, in fact, each of us could become programmers. Then, instead of getting only the functionality that makes sense on average across billions of people who now own cell phones, we could custom boutique design the functionality that we want our own assistant to give us. This would be, for me, a very useful function. So the point is there are a lot of things that are in the sensor effector closure of your system. The ones that are obviously useful for everybody are pretty much there now, or will be in the coming year or two. But there's a very large set of additional functions that are not there and are not going to be there in the next 5 years if we keep waiting for them to be inserted at the factory. All right, so the general framing of the problem is, the best I can do at the moment is this. I want to say we're given some sensor effector agent with some set of sensors and effectors, and also I'm going to assume that we can give this agent initially, an initial structure, where it has a primitive language competence, which allows the user to refer to the sensors and the effectors of the phone. So for example, if my sensor has an or my phone has an accelerometer, then I want the primitive language capability of that phone to include understanding the utterance, what's the reading of the accelerometer? Or if it has an effector like sending email, I want the initial language competence to include create a new email. Okay? So suppose we're given a system with a primitive language competence grounded in its sensors and effectors. And then we want it to learn actually a couple things. I want it to learn new lexicon entries for the language, so that if I say, for example, drop a note to Bill, and it doesn't know what drop a note means, then it can tell me I don't know what drop a note means, and then I can teach it. And I can teach it in terms of its current language capability. So I can say, oh, create an email, etc. I also want it to learn new procedures. If it snows at night, wake me up 30 minutes earlier. Again, grounded in the sensors and the effectors of the agent. If I say if it snows at night, I can ground that in the sensors of the agent. What it means is pull up the weather app, look at the current conditions, and if it says SNOW, then it's snowing. Wake me up 30 minutes early, that's easy, right? Open the alarm app and subtract 30 from whatever is there. And then I want also to be able to teach it, for it to learn from my instruction, about latent variables in the world. There are many of them. For example, I want to be able to say, define the concept course, which has a title, instructors, TAs, students, and semester. So I just defined a new type of data and the fields of that data. And then I can also tell it one course is Tom's fall 2018 class on deep reinforcement learning. So it seems to me these are, this is the way we're thinking about the problem in our group right now. So again, we're given a sensor effector system with primitive language capability, and then the three types of learning it needs to do, three types of things we want it to be able to learn, are better language capability, new procedures that we're trying to instruct it, and then new data structures and new background knowledge for its long-term memory that are essential for it to both understand and implement the instructions that I'm giving. Okay, so the best thing is really to drop out of here and show you the current primitive system that we have. But it'll give you an idea much more grounded than I can do by just speaking of what our current system does along these lines. So what you'll see is Igor Labutov, our postdoc, who's been instrumental in developing this system, have a simple conversation with our system. So you have to, the sound will work, so you can just listen.
Katie is a new member of the project team.
Katie is a member of the project team, right?
That's right.
Okay, I made Katie a member of project team.
Changing long-term memory.
Tell my project team we will meet at 4 p.m.
I don't understand what you mean by tell my project team we will meet at 4 p.m. You can explain or demonstrate if you want to teach me, or just rephrase.
Okay, I'll teach.
Great. Please break it down for me to steps so I can learn.
All right, first create a new email.
Compose a new email, right?
Yep.
An instance of type email created.
Then set its recipient to the email address of everyone on my team.
Set recipient field of email you created with the email address fields in project team's instances, right?
That's right.
Got it.
Then set it subject to we will meet at 4 p.m.
Setting subject field of email you created the we will meet at 4 p.m.
And send it.
We'll execute send this email. Got it.
That's it.
Great. I learned how to tell myself something or someone something.
Okay, now tell the assistant.
Okay, so there you saw that little snippet was Igor saying, tell my project team, blah, blah, blah. It didn't understand, and so he instructed it, and you notice that what he did was he broke it down into the steps that create a new email and put this in the recipient list and put this in the subject line and send it. Those are the primitive sensor effector commands that the system started out with, and so it was fair for him to assume that it had the language competence to know how to refer to those primitives. And so now that it has been told that it involves these 4 or 5 steps, the thing that he was trying to do first, it now has a training example of what he really meant, what was the semantics of tell my project team that we're going to meet at 4 p.m. It knows the semantics is do these 5 things, do this sequence of 5 things. And so that's a training example for it. And he now can use that in some generalization of that competence. So the system has now learned really 2 things there. One is a language capability it didn't have. It now knows what tell my X that Y means, at least in this instance. And it also knows how to. I mean, it has the procedure as well as the semantic parser capability. So now, to continue, what you'll see is he can use that now to instruct it to do similar things. I think.
Great. I learned how to tell my something or someone something.
Okay, now tell the assistant I will be busy at 4.
Tell your assistant you will be busy at 4, right?
That's right.
Done.
Executing. Tell my assistant I will be busy at 4.
If I get an email from my project team, then forward it to my assistant.
Okay, so now here's an if-then procedure.
I don't understand what you mean by I get an email from my project team. You can explain or demonstrate if you want to teach me, or just rephrase.
Okay, I'll teach.
Great. Please break it down for me the steps so I can learn.
Alright, well suppose I get a new email.
Okay. I will wait until there is a new email. What should I do?
It's a good way to advise guide your students.
Then check if the sender has an email address of someone from the project.
Check back some email address fields and project teams instances appeared in sender field of email that arrived, right?
That's right.
Okay, I will check that.
That's it.
Okay, add a rule.
Okay, so in that second example, in the first example, he's just giving a command, do this now. The system didn't understand. He could tell it what he really meant, so that next time he now can use the verb tell and assume that the system has the semantics for tell. The second example is really just to illustrate that we can also, in some cases, put together if-then procedures that result in standing rules, like things that are going to now be constantly monitored by the system, the if part. And if that triggering event occurs, then the system will do it. Notice in that case it asks for a clarification, not of everything, but of just the if part, because it actually did understand how to parse, in that case, the then part. So if you look at the transcript we just went through, we saw really 3 kinds of things. The first was really an assertion of just a fact into the long-term memory of the system. Katie's a new member of the project team. Second one was teaching it this capability for how to tell. And then the third was a simple example of an if-then. So did I see a hand here a moment ago that I ignored that wants to still go up? No. Okay. So let's look inside and see what the system is really doing. So the system is based on a semantic parsing algorithm. The first version of the system was based on a CCG parser, which I'll use here, although more recently we've loosened up on some of the constraints of CCG parsing. But the idea of semantic parsing in general that we're using is that every utterance in natural language, like tell my group that we're going to meet at 4 p.m., gets parsed not only in the way your 7th grade English teacher taught you, like into nouns and verbs and noun phrases, but in addition to syntactically parsed, it gets parsed into a meaning representation. In the case of prepare an email to Bill, here is the meaning representation. And so a key part of the system is learning a semantic parser that will put together expressions out of the words that you tell it. In Leah, that's our learning by instruction agent, these logical forms that represent the meaning are grounded in the agent's sensors and effectors. So that if you literally eval this expression, those of you who are Lisp fans, this will result in executing the command of first creating an email and then setting the recipient to Bill. So not only are we parsing utterances into logical expressions, but those importantly, those expressions are grounded in the sensors and effectors of the agent. Third, the parsing steps, as I mentioned, combine both syntactic operations like replace an adjective and noun by the non-terminal symbol noun phrase, but also the same parsing rule will tell how to combine the semantic expression for adjective and the noun into a combined expression. So if this is like yellow taxi, then the semantics there is the yellow predicate applied to the taxi, true or false. And then finally, the learning that's happening is in response to the little episode we just saw in the video, is learning that both redefines the grammar. Before that episode, there didn't used to be a grammar rule for how to parse the token tell, but now there is. And also, not just redefining the rules of the grammar, but also the parse strategy. So there's an evaluation function that determines which of the many different parses that you can legally create for a sentence is the one that you actually want. And so the system's learning both new rules to add to the grammar and revising its evaluation function for driving the building of the parse tree itself. Okay, so just to give a simple example quickly, suppose I have the sentence, set the subject to time to go. Like I might say, tell my student it's time to go. In teaching it, I say, set the subject to time to go. So to parse this, what the system will do, here we have some of the rules that are in the system that form the lexicon. And so, for example, the system could first focus on the token subject, which can refer to a field name, according to this grammar. And so one parse is to say it is indeed a field name. And then furthermore, a field name can refer to a mutable field, in which case its semantic expression is get the value of that mutable field called subject. Then we can move on to this. Well, according to our grammar, any token sequence can be viewed as a string. And so this is a token sequence. It could be viewed as a string. As I said, there are many different parses. I'm showing you the good one, and it's up to the evaluation function to drive the parse toward the good one. But then, for example, we have the preposition to, which can absorb the string to its right and essentially use its lambda expression already Then we can move on to the and set, and eventually come to this expression. So that gives you the gist of how the semantic parsing works. We're just like any parser working from the tokens to their non-terminal symbols. It's just that we have associated with each syntactic operation a semantic operation that aggregates, composes in some way the expressions of the components into a combined expression of the non-terminal. Okay, so that's the idea of semantic parsing. So you can see part of what gets learned are new entries into the grammar and a revised parsing strategy. So what I haven't said is how do we generalize from this? And so that is, for example, in the video we saw, tell my group we're going to meet at 4, but then we saw that afterwards it had generalized that expression and it could respond to then the request, tell my assistant that I'll be busy at 4. In general, let me use this example, tell Tom I'm late. If the system doesn't understand, I can say create an email, add Tom's email address, in the subject put I'm late, send it. And so that will result in that training sequence will create this composed logical expression that says literally create a new email, set the recipient list to Tom's email address, set the subject to I am late, and send it. So this becomes, now you can see from that 4-sentence instruction, we get a single logical expression that was the intended semantics of tell Tom I am late. And so this becomes the training example semantic expression for tell Tom I'm late, and the system will update the grammar accordingly. The question is, how does it generalize? These are all full of constants. In our case, this will turn into a function with 2 arguments, one corresponding to what was the constant Tom and one I am late. But in general, our algorithm is to parameterize any span, contiguous span of text in the utterance that corresponds to a simple subtree in the semantic parse. And so in this case, when you apply that to this expression, we get this parameterization. It's just a heuristic. It's not guaranteed to work. But we found that, in general, it's a reasonable thing to do. So that's the algorithm for taking the spelled out sequence of sentences, create an email and do this, send it, and turning that into a training example for what must have been the semantic intent for the original statement that the system didn't understand, and then generalizing that. Okay, so this is what happens if you try to get people to use this. We ran an experiment where we got 123 Mechanical Turk workers on Amazon. We gave them a text, not speech, version of this system. And they interacted with it. And we gave them some tasks to perform that involved reading emails and acting on those emails. For example, here's a screen that they saw. This one says, your 9th training task is to create a new email and set the recipient to the current email sender. You just received an email. Set the recipient to that email sender. And then we tell them, don't just type the email address, use the phrase current email sender. So then within that, they can say what they want. And here, the user is saying, set the recipient to mom. The agent is saying, sorry, but mom is not an email address. And the user is saying, well, set the recipient to mom's email, and so forth. So we gave them tasks to perform, and we gave them a little bit of guidance about how to interact with the system. But other than that, we let them do it. And what we found was that many subjects ended up teaching the agent new commands voluntarily, like teaching them commands like forward and reply and so forth, so that they wouldn't have to type in every time the long expansion of that, could just use that as an abbreviation. That on average, those who completed all the tasks saved a lot of time by the things that they did teach, and that sadly, less than half of the subjects actually did complete the task. So the system's not perfect, and you even noticed, I bet, watching the video that you wish that it would have gone faster. You wish that a system wouldn't have repeated back every single thing that you said and as verbosely and so forth. So there are issues, but there's also some degree of evidence here that people who are not computer programmers using the system were able to, in 40% of the cases, get through and, in fact, teach it things. Okay, so this is just preliminary system, but some evidence that there's signs of light and need for better techniques. Okay, so I want to talk about two more things. So far, we've just talked about parsing and learning the parse for a command, but in fact, learning procedures is a little more tricky. For example, I might say, whenever it snows at night, set my alarm 30 minutes earlier or whatever. But in general, the kind of procedures I'm going to teach are, if there's some sensor obtainable property, then do this effector kind of command. If we can build up a set of rules like that, that would be a good start. But if you think about it, there are several kinds of things that can go in the if part, the conditional part. One type of thing you might call, what logicians might call, closed form definitions, intentional definition of the category. Like, suppose I say, if I get a new email from Fred, well, it's easy to say what the condition is there to define it. Test whether the value of the field name from equals Fred. So that's an easy one to give a closed form definition. Others have to be an active sensing procedure. Like if it snows at night, involves pulling up an app and running some commands on it. But the trickiest ones are the ones like, if I get a spam email, delete it. Or if I get an important email, be sure I see it before I leave work. And those are tricky because the teacher doesn't really have a closed form definition of those. But still, we want to teach those, right? And so we have spent some time, and when I say we, I really mean primarily Shashank Srivastava, whose PhD thesis is specifically about how to do conversational learning of these kind of concepts. He's been working on this as part of his PhD thesis. He has a paper in EMNLP this past summer. And the problem really is, the biggest problem is that often the teacher doesn't know how to declaratively define. Teacher might know an important email when they see one, but not be able to spell it out exactly. And so the approach that we're looking at there is that the system will be able to get some labeled examples from the user and also some advice. So for example, if I'm saying, if it's spam, I might say, here's some examples of spam. Here's some negative and positive examples. But also I can say things like, if it mentions money, it's more likely to be spam. If it's trying to sell me something. If it comes from my mother, it's probably not spam. So I can give all kinds of advice, some necessary and sufficient conditions, approximate, probabilistic. I can say things like, usually, if it comes from somebody I've already sent email to, it won't be spam. That usually word is interesting. So those are the kinds of issues Shashank has been looking at. In fact, he created a data set, which is available on our website, where he had one set of mechanical Turkers define write emails that are positive examples of the 7 categories shown on the top. So for example, you have people generate 167 emails to themselves to keep note of a personal contact. And then he had a different group of mechanical Turkers give advice on how to learn that concept. Advice like, these emails usually closes with a name or title. And so forth. Messages to friends sometimes have JPEG attachments. So these were human-generated data to try out the method. And then here's the approach that he's taken. So he says, well, we're going to frame the problem in general. We're trying to learn some concept, some if part of a rule, which is just a function from some x to a Boolean value. Might be, for example, x might be emails. We're given a small number of labeled examples of that function, some emails labeled as, say, spam or not, and a set of natural language statements, n of those, each describing some Boolean property of the email, like these. These are sentences describing Boolean properties of emails. And then what we want to get out is a semantic parser for sentences, again grounded in the observable features of the email x, which assigns a Boolean value for, treats each of those sentences as some function, Boolean valued function. Is this true or false of this email? So we want a semantic parser of the advice sentences that can be grounded in some Boolean expression that can be evaluated on the email. And we also want the classifier for the concept we're trying to learn. And so the approach is really a EM-style approach. We're going to represent each x, each email, by the observed features plus the n Boolean features that we think those n pieces of natural language advice meant. And then we're going to jointly learn the semantic parser that defines those, as well as the classifier itself. So when you put that together into a block diagram, it looks like this. And so the parameters that get updated on the M step are both the parameters that define the parser and the ones that define the classifier. And then on the E step, we re-estimate what are the Boolean values that go along with those different sentences of advice that make the full data likelihood maximized. So it's an iterative procedure of re-estimating what that advice would have meant if we could get maximum classification accuracy, and then freezing the advice and updating the parser and the classifier parameters accordingly. Okay, so, and if you do this, Shashank has shown that actually works, in fact works. Here you see in red the accuracy of a classifier that's ignoring the advice and just using a bag of words representation of the emails. And you see in blue a system that uses those same examples, same training examples labeled, but also gets to use the advice. And so you see that the advice, in fact, gives a significant boost, especially when there are few examples. Interestingly, if you look at the details of this, one thing you find is that the learned parser is not perfect. But in some cases, that really doesn't matter, because if the system in the EM process, you can actually end up learning an interpretation of the advice that's even more useful than what the advisor was stating. I'm not saying that's a good thing, because in the end we want the parser to be correct. But in fact, we did see that occurring in here. And I think, if that same parser was trained across a wide range of advice and stimuli and so forth, then presumably it would tend toward being a correct parser rather than an incorrect but more useful than correct parser. Okay, so that's basically where we are. To summarize in a couple sentences, I really do think if we could make human teaching be the method of choice for certain kinds of programming, including programming our phones, then we would have a dramatic shift in the way that people and phones relate to each other. and people in computers, because people would then be able to teach their machines instead of viewing them as these frozen, given, items that are given to us. If we could actually all customize them, I think we'd change the nature of the relationship. And so what you see here is a simple first step in that direction, where the key elements are, we're thinking of the system generically as having sensors and effectors and having a primitive language capability. And then we're asking, what can we bootstrap out of that primitive capability by incrementally teaching the system more and more language competence and more procedures, both of which can then be referred to in subsequent instruction. Okay, the final component of this is, why don't we also just teach by demonstration? And it turns out we have a companion project led by Brad Meyers in our HCI department, which is looking at the same kind of problem, but from a programming by demonstration kind of perspective. And I'll show you the video that Toby Li, the PhD student, I just have to warn you that I asked Toby for a short video, and he had a long video, so he just sped it up. So you have to listen carefully.
His effector work.
It was very effective. Okay, here we go.
Order a cappuccino.
Order a
Sorry,
cafe.
but I don't understand. Would you like to teach me? Say yes or just ignore.
Yes.
Great. When you say, for example, order a cappuccino, what shall I do first? Say demonstrate to demonstrate.
Demonstrate.
Whenever the user gives the agent a command that the agent cannot understand or doesn't know what to do, the user can teach the agent by demonstrating how to perform a task using any third-party apps installed on the phone. In this example, the user demonstrates how to order a cup of cappuccino using the Starbucks app.
Order a cappuccino.
Executing.
The agent learned the task and is now able to automatically manipulate the Starbucks app to order a cappuccino for the user. From only one example of demonstration, Sugarlight can also determine the parameter in this task from the user's voice command and find all the other drinks it can order from Starbucks by analyzing the structure of the app's user interface. As you can see, the duck icon on the screen is now clicking on behalf of the user to order a coconut milk mocha macchiato. This work will appear in Kai 2017 and was supported by Yahoo through CMU's Inline project.
Okay, so that's just a glimpse, but you get the idea. Obviously, if we're going to teach our phones, we want to be able to demonstrate certain things. Like if I'm teaching you how to recognize whether it's snowing at night, it's easier just to say, look, I'm pulling up the weather app and here are the current conditions right there. So what we have at the moment is a beginning verbal only kind of instruction and a beginning demonstration only kind of instruction. But obviously where we want to move is toward integrating these. And so we've begun collecting data where we have people in a Wizard of Oz kind of experiment where there isn't really no computer behind there, but we just have them teach us by showing and telling, by demonstrating and explaining. What you see people do in this data is they'll say things like, oh, I'm teaching you how to order a cappuccino. Here I'm pulling down the menu, there's cappuccino, but obviously you could choose anything in this menu. So in some cases, people are actually giving verbally clues about how you should generalize this procedure. They're telling you which of the constants in this should be parameterized and where to look for some of the alternative parameter values. They say, oh, here I'm paying with credit card, but obviously you could use PayPal right here. There's a button for PayPal. So that's the kind of show and tell, demonstrate and speak kind of instruction that people tend to give. And so we're hopeful that if we can put these things together, it will be even more useful. There are a whole bunch of research issues that then come up. What if you teach your phone, then should I have to teach it the same things? No, we should have community learning. But then what if you teach your phone that tell Tom I'm late means send him an email, and what if I teach mine, tell Bob I'm early means to send a text message? Then we have conflicting semantics, and there are a bunch of questions around how to deal with that. What if I say if it snows at night, wake me up earlier, and the system does, but it only snow flurried? It's like, I don't want to get up early for that. Oh yeah, I forgot to tell you. This is one difference between teaching a person and teaching a computer. If I taught you to wake me up, call me 30 minutes early if it snows, you will know that I really intended to say, if it snows enough to mess up traffic, then. But I don't say that actually to you as a human because I know you have common sense. So that's an issue. But maybe one way around this is for me to say, if it snows at night, then wake me up 30 minutes earlier because I don't want to be late for work. If I can give you the because, then at least I'm giving you the rationale for the procedure, and you have a notion of ground truth, if you've got enough reasoning capability and common sense, I've basically told you the procedure in two ways. I've told you, wake me up, but I've also said, don't let me be late for work. So I think one direction we're very interested in is whether providing these kind of rationales can help the system think through and get to the appropriate generalization. And again, in the spirit of a conversational system, it might even want to ask clarification questions. Like, if you don't want to be late for work, should I then not worry about Saturdays when you don't go to work? So mixed initiative dialogues would be a great direction. Clarification dialogues, there are plenty of times when the system misparses what you just said. It'd be nice to come back to it and say, that's not what I meant this. Right now in our system, that's not easy to do without just canceling out of the whole thing. And beyond combining verbal with demonstration, it also is possible in general for sensor effector systems to do all those other things, like run experiments. If I'm teaching certain types of procedures, the system might even want to experiment with ways of achieving the purpose, and in that way be able to guide its generalization. So these are the kinds of research issues that lie ahead. If you get anything out of this talk, here's the message that I think is honestly the correct message to get out. We're spending ridiculously little time in all the massive amount of research that's going into conversational AI systems. We're spending almost no time on using conversations to actually teach our machines. And that's what we as individuals really want. So the message is, here's a wide open research area. There's almost zero work in this area. The potential, if it was successful, is huge. And so those of you who are looking for a PhD thesis, I recommend you consider this. Thank you.
I'll take the first question. So it seems that, I was going to ask you first about what happened if there's just 5 minutes of snow, and then you address it. But it seems that we're kind of knowing there's a huge knowledge base out there in the world. I think of what Watson has done. I just go in Wikipedia and all the web pages. So it seems that we should be able at this point, the agent should be able to go and figure out by itself without me having to explain kind of, no, only if it's a work day and only if enough snow has gone down. You should go out there and read the vast, just all the novels in the world and kind of learn from that snow is only problematic on a work day if it messes up the traffic. And we're not taking advantage of all the knowledge out there. And we take advantage of this knowledge.
Yeah, that's an excellent point. You're right, it's out there in text form on the web. Projects like Watson have tried to make that more computer interpretable, and it's a key part of what these future systems are going to have to do if they're going to have common sense. That's a large part of what common sense is. So I couldn't agree more that that's something we need to do. I will point out that I could imagine two people saying to the system, if it snows at night, wake me up 30 minutes earlier. One person, let's say, who lives in the north, might want it for traffic, might implicitly be thinking, because I don't want to be late for work. Somebody who lives in Houston might say, because I see snow so rarely, it's fun to go out and make a snowball and play with it. The common sense, so it's not just a matter of common sense reasoning, it's also a matter of estimating the purpose.
No, but I would argue it is common sense, but the more nuanced common sense.
That's
right?
fair enough.
So we kind of seem to go at the end into this really knotty problem of common sense reasoning.
Yep, it's true. And I mean, the cool thing about this example is that you could imagine a Watson-like system trying to extract all this knowledge from the web to build up that common sense. You could also imagine that if it tried to do that, it would fall short, partly because there's such a diversity of common sense out there, it's hard to get it all right. It probably wouldn't have exactly the common sense that people in the South are more likely to think snow is fun, people in the North think so. It probably wouldn't have it all. But it would have, let's say, 80-20 someday. The beautiful thing is a short conversation can then clear it all up, right? So I think if many of these things we're trying to do fully automatically in AI, I think once we get to kind of 80-20 solutions, that plus a short conversation can kind of get you to a workable 100% solution. And so I think, and that's one reason why I think over the coming decade, we're going to see more and more, I hope we're going to see more and more work where we think of learning as not purely this thing that must be totally automated from a set of data that we collect from the web and be perfect or near perfect, we must put up with it, which, by the way, is exactly how our phones learn from us today, right? They watch what we buy and they don't talk with us about it. Then they show us advertisements. It's totally passive data collection and they're trying to guess. But a short conversation could clarify that, oh, you know what? I already bought the ticket to Morocco. You don't need to show me any more cheap flights to Morocco. I think if we really thought as users that a conversation with our device would have a good outcome, it would be easy for us to generate the motivation to do it.
Other questions?
Thank you for the inspiring talk. So my question is, what's the main technical challenge to achieve the conversational machine learning?
Great question. I think there are several, and I'm not sure I know all of them, but to me, the scariest part of this is actually scale is very scary to me. So we have a system we've used, several of us have used this in the way you saw, to teach it one thing or another thing. What we have not done yet, and which I'm afraid of, is what if we now give this to 20 of our friends and have 100 times as much stuff taught? What I don't know is, will the natural language understanding part actually scale up? Because it turns out natural language semantic parsing is not easy. The miracle is that it manages to work in these examples that we've run so far. But part of the reason is we've made the problem easy by the system not having a very complex grammar to begin with. It does know about the sensors and the effectors that we're conversing about, but not very much. But now once it knows that, once we've taught it a bunch of things and it's added, let's say, 10 times as many grammar rules as it started with, Now the complexity of that parsing problem is going to be much worse. And I really am nervous about whether we'll be able to scale a successful parsing strategy as the grammar must grow in complexity. So I'm really worried about that. I think also the list of things that I put on the next to last slide are all things we really haven't looked at yet. But some of those actually strike me as making the problem easier, and some of them make it harder. I really do think if we could do mixed initiative conversation, where instead of the user dictating in the system saying, is this what you meant, is this what you meant, if we had an interactive dialogue, I think that actually makes the learning problem easier. So, the complexity of the parsing is one thing I'm worried about. That's going to get harder. But maybe if we can have interactive dialogues, then the system can ask for advice about how to generalize, and so did you mean this, and so forth, then that might actually make it easier. So I think as a research strategy, we want to kind of take on a blend of these necessary scaling problems and adding new functionalities which hopefully will make the problem more solvable, less unconstrained.
Yeah, thanks again for coming today. I guess I don't trust my machines very well, very much. And so how do you build in protection for false positives, false negative type things, especially in categorization? Like if I tell my app to forward an email that seems like it should go to my boss, and then my wife sends me an email saying, you're working late again, your boss sucks. Something, that's a silly example, but something like that. Everyone still checks their spam folder, especially at their work email, because you can't miss that important email, even though only 1 out of 100 maybe is wrongly classified. So how do you protect from that happening in something like this?
Yeah, that's a great question, great point. I agree 100% with it. I don't think that we will trust these systems initially, especially when, especially we've only given them a couple examples and had a brief conversation. We will want an interface where before even if they detect a condition like an email containing the word boss, we'll want them to just suggest it and we get to click yes or no. So in that way, we'll want the bucket to stop with us on these until we trust them. In fact, it's been over a year since I checked my spam filter. Yeah, honestly.
That's
so,
why I don't reply.
My students have a different interpretation of that. But I think we do build up trust at some point and kind of go with it. But it takes the experience of building up trust.
Thank you. My question is that it seems that semantic parsing is the key module in the system. So I was wondering that is there any possibility that to learn a parsing system instead of manually define a parsing system in a subsystem in the whole system?
Yeah. Great question. We are looking at deep network sequence to sequence kinds of parsing strategies. So far, this works way better, but we're looking there. And your point is a good one. One thing that makes this work better at the moment is the grammar is very modular here. And in response to a particular training example, like tell X that Y, it's easy to identify locally what the problem is with the grammar. And so adding a new lexicon entry, a new grammar rule that defines the verb tell to be this effector procedure is a very modular operation. And in the deep network approaches, things are not so modular. And maybe that will change over time since there's a lot of work in that area. But right now, that's the reason why this does better than the kind of, say, sequence to sequence kind of models that we've been looking at.
All right. Thank you, Tom. I have a feeling that in order to make this conversational machine learning system to work well, to be helpful, it would be helpful if we can build a sort of like the worldwide knowledge database built based on some predefined knowledge schema so that everyone can add their own knowledge into the system. Let's say I mean something A equals something mentioned by something B mentioned by Moshe, and people can vote on the same thing. Like I say a type of drink that can wake me up. So a lot of people may vote coffee and some people may vote tea. So if we build such kind of a worldwide knowledge storage, storage so that we can use those storage to back up those conversational machine learning system on any kind of platform. So I just want to know what is the current status and the plan in the machine learning community.
That's interesting. I think I come down somewhere close to you, but not exactly where you are. I think there is, as Moshe was suggesting, plenty of common sense that's generic that you should know about. Like, if it snows, it messes up traffic. It's like just a fact. Hardly anybody would argue with it. It's just accepted. Then there are things like preferences. Like, would you prefer coffee or tea? And those are kind of idiosyncratic. I guess there's a factual part of that. One of those has more caffeine. I'm not sure which, but there is factual information about different teas and how much caffeine they have. But the fact that I would prefer coffee in the morning is just kind of a personal idiosyncratic thing. And so there is plenty of work, like the Watson work. We have a project called our Never-Ending Language Learner, which is trying to read common sense off the web. But I think in the end, what it's going to come down to is that there will be some person-independent common sense knowledge that needs to be referable, needs to be available to resolve, among other things, semantic parsing ambiguities. But at the same time, there will be a local inside your phone overlay to that, which is your personal knowledge base, which you might not even want to share with the world, and which also has your idiosyncratic preferences and beliefs, and things like your own definition of whether tell means to send a text or an email and so forth. So I think it remains to be seen where that dividing line is, but I think there will be a blend of those two, sort of population-wide knowledge, which is mostly factual, and then idiosyncratic knowledge / preferences / way we think about things. That'll be local.
Thanks, John. You made me think, and that's really nice on a late afternoon. So I was thinking that we program our own young conversationally. It's a huge component.
Yeah.
But it's not just conversation. It's sort of demonstration. I'm thinking back to a first grade classroom or a kindergarten classroom. I think our machines are about at that level. We want to be able to instruct them to do things. And I think we have, as a species, a huge wealth of information on what goes wrong there, how we can be effective there. We've certainly not cracked the code in terms of being able to get 80% performance, I think, even at that level. So what can we learn from that? I mean, what do people who do that every day for a living have to tell us about making conversational machines? In the sense that maybe they have some insights. You know, we want someone to be able to add, subtract, and recite the alphabet or whatever. How do they go about structuring that task? Perhaps we have something to offer to this conversation.
Yeah, I know next to nothing about, child development education, but I do know that people have identified strategies that people automatically use without even thinking. So for example, if I'm teaching you a language and I say, I have to be, if I hold up something, this, and I say, this is Greek, and then I hold up another one that looks just like it, but it's a different color, and I say, this one's group. then you assume that it's the color that I'm talking about. But then I can hold up anything. Doesn't even have to be another watch. I could say this one's white, and you'll know that I'm referring to color because there is this kind of implicit strategy that humans use with each other, that if you're teaching, say, words in another language, you just automatically fall into picking a feature and establishing that that's the feature, and then you can rattle off the whole vocabulary. So there's just a simple example out of what people know about how people teach people, that surely we won't want to, I mean, if the whole goal in this line of research is to make it easy for everybody to be a programmer by just teaching the same way we teach each other, then surely we will, if we get to that day, we'll have systems that experience the same kind of teaching strategies. And that's probably a good thing, and if we know about them, then the system can, in fact, take advantage of those by knowing what those strategies are. I'll just say there's a conference or a cluster of conferences in London at the end of June called the Festival of Learning, which doesn't mean the Festival of Machine Learning. It means the Festival of Computer-Driven Education. And they asked me to come to give a talk. And I said, well, I can't really because I don't know anything about that. And they said, well, you can come talk anyway, as long as you can think of a title that sounds relevant. So I gave them the title, What If Computers Could Teach People? And I'm going to give them a version of this talk. But I'm hoping that at that conference I'll actually get to, learn some of these techniques that you're referring to.
Let's thank Tom for an inspiring talk.
Thank you.